This is a video for AQA Further Pure Mathematics, Algebra and Graphs section 5.3, which is looking at finding areas enclosed by polar curves. You should be very familiar with the formula for the area of a sector of a circle, which is A is equal to a half r squared theta. Remember here, theta must be in radians, and therefore the fraction of the circle that we have is theta over 2 pi, where 2 pi radians is the complete circle. Now this idea we can use to help us to calculate areas which are enclosed by a polar curve. This example here shows that we can consider this area that's shaded in red as being a sector where the radius is variable. But if we consider a small element of that, so if we take an element where we've got a very small angle, let's call it delta theta, then the radius is constant, or can be thought of as being constant, on that small change in angle. So therefore the area of this element here is going to be 1/2 r squared delta theta. So that the full area will be the sum of that. So we can say that the area is going to be approximately equal to the sum of all such elements, which is 1/2 r squared delta theta. But in the limit, as delta theta approaches 0, we can say that the area then will be equal to an integral, which is 1/2 r squared d theta. Now if you want a more formal proof of that, then you should be able to find one in your textbooks or online. So to calculate the area then, we need to calculate the integral of 1/2 r squared d theta, and that will be between theta from, in this diagram here, if I call these theta 1 and theta 2, so you can see the theta's changing from some value theta 1 and theta 2. So let's look at this in a particular example then. So we're asked here to find the area enclosed by the curve r equals sine theta between theta is pi by 6 and pi by 3. Now although not strictly necessary, it is helpful to have a sketch. So this is the curve r equals sine theta. Remember that's a circle, and the value of theta is equal to pi by 6 is this line here, and theta equal to pi by 3 is this line here. So this is theta is equal to pi by 6, and here theta is equal to pi by 3. So theta equal to pi by 3. So the area that we're trying to find is the area enclosed between the curve and those two radii. Now we know that the area will be equal to the integral from theta 1 theta 2 of 1/2 r squared d theta. So we simply need to substitute what we know into that. This will be equal to the integral from pi by 6 up to pi by 3 of 1/2 r squared is sine squared theta d theta. Now this is always going to involve r squared, and by the nature of polar curves, often you're going to be dealing with things like sine squared to integrate, and therefore trigonometric identities are going to come into their own. So taking out the half inside the integral, then we can use the trigonometric identity so that we've got the integral from pi by 6 up to pi by 3, and then inside, instead of sine squared theta, we can write that as 1 minus cosine 2 theta over 2 d theta. Now that's something that we can then integrate, so we get 1/2 and the integral becomes of 1 over 2 becomes theta over 2, and then cos 2 theta over 2 is going to be equal to sine 2 theta divided by 4. And we're evaluating that between pi by 6 and pi by 3. So we've got a half outside a bracket, and then substituting the value pi by 3 first of all, we get pi by 6, and then minus, we've got sine of 2 pi by 3, so that is root 3 over 2. We're dividing that by 4, so in total root 3 divided by 8. Then substituting the value pi by 6, so we get pi by 12, the first part, and then 2 times pi by 6 is pi by 3, so we therefore get sine of pi by 3, which is root 3 over 2, so again we've got minus root 3 over 8. Now if you look at those, we've got negative root 3 over 8 in the first bracket and the second bracket, so those are going to cancel out. And pi by 6 minus pi by 12 gives pi by 12, and a half of that, so we get a final answer of pi by 24. So there it is, so we just look through it again on this neater version. We've got the formula which says that the area is the integral from theta 1 to theta 2 of 1/2 r squared d theta. So substituting r into that, and then if necessary using, in this particular case, a trig identity to change the sine squared into 1 minus cos 2 theta over 2, and then evaluating the integral. Now it's just worth thinking about whether the answer that we've got, pi over 24, is sensible. Well, we know that this is a circle with radius equal to 0.5, so the area of the circle would be pi r squared, so that would be 1/4 pi. That's for the full circle. So we've got something which is about 1/6 of the area of the circle, and certainly that looks about right for our diagram. Well, that concludes this video on areas in polar curves, and indeed concludes the series of videos Algebra and Graphs section 5.